Okay, now it's recording. Thanks for the reminder. That's funny. Thank you, Myra. All right. Cool. If y'all have additional methods, you can share that at the end of class. For now, we just want to go ahead and make sure we get through everything. So for the last two digits, what we're doing is we're taking the difference from 50 and squaring it. So 56 is 6 away from 50, so we square that to get 36. Shreyansh, hopefully that answers your question. Okay, awesome. Danush, go ahead.
So how do you get the first two digits in?
So to get the first two digits, you add the difference from 50. So um, if we look at this case 56, the difference from 50 is going to be 6. So we add that difference to 25. So I do 6 plus 25 to get 31, and those are my first two digits. Yeah? Okay, awesome. Okay, Iran, if you want to share your method later on, you can do that. I just want to make sure that we get through all the main content first, but you're welcome to share at the end of class. Um, okay, Sumanbi, I'm not sure what that technical issue is. Is it like an audio thing or can you not hear me or can you not see me? And then also, okay. So Vaibehi, you add to 25 when your number is greater than 50, and you subtract from 25 when your number is less than 50. So hopefully that answers that. Okay, awesome. Let's go ahead and move on. So we're going to transition away from multiplication. I know last class we did a lot of multiplication, and we started with multiplication in this class. But today we're going to cover a wide variety of topics. So transitioning away from multiplication, we're going to start looking at fractions. So fractions, decimals, percents, all the things. I know that's pretty scary. Oh, okay, Simonvi, right now, okay, so you shouldn't be able to see any recording right now, but like if you have issues accessing the previous recordings, reach out to me after class and we can sort that out. Okay, awesome. Perfect. Okay, so like I said, we're gonna be taking a look at fractions, decimals, and percents. To start off, let's take a look at some fraction properties. So there's this cool thing with fractions. Okay, well, I feel like a lot of people are scared of fractions, so hopefully we're going to make them very approachable and easy. So yeah, let's start off with like a cool thing about fractions. It's expressing fractions in different forms. So I'm going to try to express a fraction as kind of like a sum of two other fractions. So do you guys agree with me when I say that 1/2 is equal to 1/3 plus 1/6? Does that seem like a true statement? Yeah, it is. Because I can write 1/3 as 2/6. So that's how I get 1/2. Now, can I do 1/3 is equal to 1/4 plus 1/12? Is that a true statement? Make sure you guys are converting the denominators. Yeah, it should be because 1/4 is 3/12 plus 1/12, and this is 4/12, which simplifies to 1/3. Okay, awesome. Now, let's say I look at an even bigger fraction. Like, let's say I look at 1/10. Do you think this is true? What do you think? I see conflicting answers. Okay, well, if we check, we can see that this is 10/110 plus 1/110. So if you simplify, you get 11/110, and that's 1/10. So yeah, that's actually a true statement. And you must be wondering, like, how did she figure out these two random fractions that added together? Well, the trick is I have a formula for it. So if I have a unit fraction 1/n, I can write this as a sum 1/n plus 1 plus 1/n times n plus 1. And you must be wondering, like, okay, where did this come from? Like, why is this even here? So let's talk about it. This one is very easy to prove. Basically, we just want to get a common denominator. So on the right-hand side, we can rewrite this fraction as n/n times n plus 1 plus 1/n times n plus 1. And if we add that, we get n plus 1/n times n plus 1. So n plus 1 and n plus 1 cancel out, and we just get 1/n. So that's how you know that this is actually true. And we call this property an Egyptian unit fraction. So all unit fractions can be expressed in this form. And I think it's pretty cool. You won't see any questions asking you explicitly about Egyptian fractions, but sometimes this is an important step in problem solving. So I just wanted to show you all this. Okay, awesome stuff. So let's take a look at a couple of other ones and see if you guys can write the conversion yourselves, and then we can move on. So yeah, how can we write 1/4 as the sum of two unit fractions? And then how can we write 1/7? Okay. I see a Rob and a phone number. Okay. And then also Pranay are saying 1/5 plus 1/20. Okay, and I would agree with this because I add 1 to 4 to get 5, and then I do 4 times 5 to get 20. So I agree with this. Now, what do you guys think for the second one? Oh, I think Anviti, Sriram, a couple of other people, awesome, are saying 1/8 plus 1/56. Once again, I agree with that because we add 1 to 7 to get 8, and that gives us, and then we do 8 times 7 to get 56. So that gives us 1/7. Okay, awesome. So pretty cool stuff. I just thought this was a fun trick and oh, okay, awesome, awesome. I think you should be able to change your name. Let me see if that's actually a thing. Yeah, I think you should be able to rename yourself if you want to try that out. Okay, awesome. So yeah, pretty cool trick. That's pretty fun. So I just wanted to share that. Sharanya, go ahead.
So like so like for the thing do you just like find a multiple of the bottom number and just figure it out, or is there like
So to find this two different fractions, what you do is you add 1 to that denominator, and then you multiply the two numbers together. So for example, when I was doing 1/7, I added 1 to 7 to get 8. So 1/8 was my first fraction. And then I did 7 times 8 to get 56. So 1/56 is my second fraction. Does that
okay?
make more sense?
Yeah.
Yeah? Okay, awesome. All right, perfect. So that was fun. I hope hopefully that like made fractions a little bit more interesting to you because we're gonna transition into some more like crazy stuff. We're gonna talk about converting fractions to decimals and percents. And this is very, very important. So if you've been zoning out a little bit, now is the time to totally pay attention. But before we move on, Niranjana, what's your question?
So for the first question, the answer you said was 1/2, but 2/6 is divided by 2 is 1/3.
Yeah, so we actually expressed 1/2 as 1/3 plus 1/6. So this is equal to 2/3, or sorry, not 2/3, 2/6 plus 1/6, which is 3/6, which is 1/2. So yeah, that was actually a correct conversion. Okay, awesome. All right, so let's take a look. Yeah, like I said, being able to convert like from fractions to decimals to percent, very important stuff. You see it all the time in number sense and also in a lot of different problems. So we're going to spend a little bit of time on this. Essentially, percentages and decimals are different ways to write rational numbers. Remember from our first class that a rational number is something that can be expressed in fractional form. Yeah, so it's something that we can express in fractional form. And sometimes we don't want to work with fractions. Sometimes we need to work with a percent or we need to work with a decimal, and it makes the math easier. So being able to convert is very important. So for example, if I had, let's say I had 8/25. Well, actually, let's do 1/4. That's a fraction, right? How do you guys think I can write that as a decimal? What do you think? 0.25. Yes, good. And then how do you think I can write that as a percent? Yeah, that's 25%. Good. So I think it's pretty easy to see that like decimal to percent conversions is pretty easy because you're just like multiplying by 100 to get your percent. So nothing too crazy there. It's the figuring out like how do I get from a fraction to a decimal that's kind of wonky. So that's what we're going to focus a little bit on. In this case, I think someone made a very nice comment earlier. Let me see if I can find it. Wow, you guys are really good. Okay, yeah, so Pranay said a fraction over 100 is basically the decimal, and I absolutely agree with that. So what we want to try to do when we're converting between like fractions to decimals is we want to get a denominator of 100. And the reason why that is because if you think about it, fractions are kind of like parts of a whole. And for us, our whole is 100. It could be 10 or it could be 1,000, but typically we use 100 as that whole. So if you think about it, 1/4 equivalently is 25 over 100. Do you guys see where that comes from? Why that's correct? Yeah? Okay, awesome. And so 25 over 100 we can write as 0.25 because remember, anytime we divide by 100, we just have to move over two decimal places. For those of y'all who don't see like why 1 over 4 is equal to 25 over 100, all we're doing is multiplying both the numerator and the denominator by 25. So that's still an equivalent form. Okay, awesome. So that's kind of like the basics of how this works. But then sometimes you might get like crazy things like 1 over 6. And then you're like, okay, how do I get a denominator of 100? Because like 6 doesn't divide 100. It's not a factor of 100. So where am I getting 100 from? And that's what we're going to talk about, these weird fractions that are kind of difficult to convert. So let's take a look. Okay, perfect. Yeah, so well, actually, before we approach this, let's take kind of we'll kind of explore some other different fractions and then see if we can work our way to this because it's kind of a big task to approach at the very beginning. So we talked a little bit about how to convert a fraction to a decimal. We kind of want to get that denominator of 100 because remember also a percent is a ratio expressed as a fraction of 100. So that's why we try to look for denominators of 100 because we want to, it's very easy to convert into percent form. So yeah, remember, percent is per 100, so cent is 100 per 100. That's an easy way to remember that. So for example, if I had 1/2, what percentage is this? 50%, good. What about 1/5? What percent is that? 20%. And what about 1 over 25? 4%, good. So if you notice, the denominator and their percentage kind of multiply out to 100, and that's not a coincidence. It's meant to be that way. So that's an easy way to check like if you're converting the right way. Awesome. Okay, we'll pause here. Rich, do you want to go ahead and ask your question? You want to go ahead and unmute? Okay, while we let you unmute, I'm going to go ahead and move on. And then we also talked a little bit about converting decimals to percents. To convert a decimal into a percent, you just multiply your decimal by 100 and add in a percent sign. So for example, 1/2 is 0.5 as a decimal. But once we multiply it by 100, we get 50, and then we add a percent sign at the end, so 50%. So decimals to percents is easy. Fractions to decimals is a little bit harder. So, yeah, let's talk about that. Well, first, we'll talk about how to convert the fraction n over 20 to a percent. Now, over here, well, first of all, what is 1 over 20 as a percent? Yeah, it's 5%, based on what we had just done earlier. So all we're doing to get this as a percent is 5n, and then you add a percent sign. So yeah, nothing too crazy there. Similarly, with n over 25, what do you guys think is going to be the percent? 4n, good. Because 1 over 25 is 4%. So like n over 25 is going to be 4 times n%. So this kind of shows you how you're able to use like nice denominators like 20 or 25 to get like nice percentages. Okay, awesome. So in like fractions and decimals and things, we have two kinds of fractions. So we have fractions that create a decimal that is finite and it terminates. So that means I can literally write out with my hand all the digits in the decimal. So for example, 1/2, that creates a terminating representation because I could do 50%. I can write out all the digits in 50. Yes, if you add zeros to the end of a decimal, it's still the same form. Yeah, so 0.5 is equal to 0.50. Yeah, okay, awesome, awesome. So yeah, let me write down the definition. So terminating means that the decimal, whoops, form ends. And then non-terminating decimal is infinite. So for example, like we talked to infinite, there we go. Sometimes spelling is hard. Yeah, so pi is not terminating because it just goes on forever and ever. Pi is also not repeating. So some non-terminating decimals can be repeating, but pi is not repeating. There's no pattern in its digits. So yeah, cool. So what do you guys predict are some fractions that have terminating forms? What do you think are some potential fractions? Do you want to list them out or list out some patterns? Okay, so I saw someone, I think Danush put in 1/3. So 1/3 is actually 0.33333 going on infinitely. And because it goes on infinitely, I can't write all the threes, so it's non-terminating. So 1/3 doesn't really count. I do see a lot of people putting in 1/2, and then I see 1/4 as well, and 1/5. So 1/2, 1/4, 1/5. I think I did see 1/9, and 1/9 is actually 0.111, repeating forever and ever and ever. So because it's infinite, it is not a terminating decimal. Yeah. All right. Is 1/20 infinite or finite? What do y'all think? Yeah, okay, I see it now. All right, yeah, so 1/8 works, 1/25, 1/20, all of these things work, and that's absolutely correct. And the reason why they work is because they are able to divide or they have common factors with 100. So if you look at it, all of the fractions I've listed out are either factors or powers of 2, powers of 5, or some combination of both. There is no 3 factor or 7 factor or anything like that, because once you introduce 3s and 7s and 9s and all these other different prime factors, you start getting non-terminating decimals. So for a terminating decimal, the fraction representation has to have in the denominator only some form of powers of 2s or powers of 5s. Okay, awesome. Samanvi, you want to go ahead and ask your question?
Is infinite does terminating numbers have to have like a pattern or something?
No, not always. So like we said with pi, pi is not terminating, but pi also doesn't repeat. It literally is just a random series of numbers. So non-terminating does not have to have any pattern. Awesome. Arish, you want to go ahead and ask your question? Let's see if your mic works now. Okay, I don't think I see it. I'll skip over you and I'll go to Udvik, and then if we'll come back to you.
Can you explain what non-terminating means again, please?
Yeah, so non-terminating basically means there's a number of digits in the decimal that I can't write out. Like the decimal goes on forever. So for example, if we look at pi, pi is like 3.141529 and then a bunch of random digits after that. Like I don't know what all the digits are of pi, and pi goes on forever. Like the decimal representation never ends, so that's why it's not terminating. Does that make sense?
Yes.
Okay, awesome. Shreyansh?
If the denominator isn't divisible by 100, will it be non-terminating?
Good question. So just because the denominator doesn't divide 100 or isn't divisible by 100 does not mean that it's non-terminating. For example, if you look at 8, 8 is not a factor of 100, but it's still terminating. And that's because 8 can be expressed as 2 to the power of 3. So any number that is expressed in terms of powers of 2 and powers of 5, or some combination of them, is terminating. However, if you have like a factor of 3 or 7 or something, then it's non-terminating. So hopefully that makes a little bit more sense. Okay, Arush, do you want to see if your mic works now? Okay, here's what we can. Oh, 9-2. Sorry, guys. As you can see, I clearly don't know the digits of pi. I really only remember 1415. All right, 9-2. Cool, cool, cool. Wow, you guys are really good at this. Okay, Arish, we can ask your question at the end of class, or if you want, you can send it to me as a direct message. Okay, Tanvi?
So, by if you like mean what's like in the fractions, when you were like explaining it, what would you mean by like the terminating and non-terminating?
So remember, terminating means that the decimal ends. I can write out all the digits in the decimal. Non-terminating means that the decimal is infinite, and I can't write out all the digits in the decimal. Does that make a little bit more sense?
Yeah, and I also had another question.
Yeah.
So like how would you like get the number that
What do you
you
mean?
have to like how you got like one half?
Yeah, so what we want to do is we want to try to get a denominator of 100 or some multiple of 100. So for example, I can write 1/2. Oops, let's switch colors. I feel like I've been writing in red too long. I can write 1/2. Okay, whoever's spamming pi in the chat, please stop, or I will like literally remove the chat for everyone else. Yeah. Okay, so 1/2, I can multiply both sides by 50. And I get 50 over 100. And remember, anytime we have 100 in the denominator, we can just move over two decimal places. So I get 0.50. So that's how we're able to convert. Awesome. All right, the other questions, let's save for the end of class. So if you guys want to write that down or send it to me as a direct message, we can address those later. Okay, awesome sauce. So I'm going to give you guys a nice chart with all of the decimals and conversions that you have to know. Hold on. Let's minimize this first, though. Okay, perfect. So, all right, here we go. I think this chart that I'm about to give you guys, everything in it should be memorized. Oh, oh no. Hold on, that's weird. Okay, it should be memorized because these come up a lot. So some of them are easy to remember, like 1/2, 1/4, 1/5, 1/8. But 1/3 and 1/9 don't come up as often. So I would recommend you remember those. Like we said, 1/3 is going to be 0.333 repeating, and then 1/9 is 0.111 repeating. Also, this chart will be in the handout for you guys to reference later, but I would definitely familiarize yourself with this. So if you're looking at these, or actually, hold on. A couple numbers are missing. So we have 2, 3, 4, 5. We're missing 6. So we can write 6 as 0.16667. Or actually, technically, it's like 6 repeating. So yeah, the 6 repeats on forever and ever and ever. But yeah, this is actually found, like if you want to divide the 1/3 by 2, you can get to that form of 1/6. Now, you'll see 7 is also missing, and 7 is really interesting. I think 7 is a cool decimal. So it's probably one of the most interesting fractions because of all the weird properties it has. So let's take a look at this. We can write 1/7 as 0.142857. Now check this with a calculator. Divide by 100, you'll see that it's 0.142857 repeating. So this is a repeating and non-terminating decimal. Yes, I would remember all of these fractions, by the way, for those of y'all asking. Yeah, so can you guys tell me what 2/7 might be? What do you think? Dave, now go ahead. Do you have an answer? And Diksha.
I actually have a question.
Okay, do you want to save your question for the end of class just so that we can get through all the content first, and then I'll stick around and answer that?
Okay.
Awesome. Okay, I see Danush put 0.28. Check the rest of your digits. I think the last four are wrong. I see Abhyuk put 285714. I think I agree with that. Cool. Yeah, Neuronjana put the same as well. So yeah, basically, it's this repeating. And you can check that by just multiplying this decimal by 2. Yeah. And so this is kind of interesting because if you look, the same digits in 1/7 are present in 2/7. And if you look even closely, you'll see that the digits kind of look like they're stuck together, like in a cycle almost. For example, if I start at 2, I go to 2, 8, 5, 7, and then I circle back to 1 and then 4. So 285714. Now, what is 3 sevens? Let's see if this pattern still exists. What do you guys get when you do 3/7? Shreyans, check your math. I think that's for 4/7. Or Arav, I agree with that. It's 0.42 8571. Repeating. Now, would you look at that? We have 4, 2, 8, 5, 7, and then we circle back to 1. It's the same 6 digits in a cycle. So not only is 1/7 repeating and non-terminating, it's also what we call cyclic. So 1/7 is a very, very interesting fraction. Yeah. Okay, Dunja, you want to go ahead? Do you have any questions about this topic?
I don't have a calculator with me.
That's okay, no worries at all. You should have one on your computer though.
That one I can't find how it can work.
Oh, that's okay. I just wanted you all to see like where 1/7 was, but it's okay. You don't need to have one. Okay, awesome. Perfect. And then Sharanya?
So like everything if we know like the past what the past thing is, do we just double it to find out the next?
No. So the reason why we doubled in this case is because it's 2/7. So that's 2 times 1/7. So we multiply the decimal by 2 as well. And that's how we get 0.285714. If we were doing 3/7, we would do 3 times 0.142857. And that's how we get 0.428571. And then you just keep on going like that. Also, some of you guys are asking about the notation. Yeah, so the bar on top shows that this is repeating. Yeah, I feel like I covered that once, but just in case I didn't, the bar on top shows that it's repeating. Okay. Yeah, 22/7 is an estimation of pi. So if you look at that, 22/7 is actually equal to 3 plus 1/7. So this is 3. And then we said that 1/7 is 142857. So that 1/4 part is similar. That's why 22/7 is an estimation. Yeah, so it's not equal to pi, it's an estimation. Yeah. Okay, awesome. Samanvi, I'm gonna ask your question.
So like what if you get all the way to like where you have to start from like when you're doing it with 1/7, when you start with like 14285 because you circle again?
Yeah, so because it's repeating, like 1/7 is 142857, 142857. And then because there's 6 digits exactly, each like number kind of starts with a different digit. So 4/7 will start with 4/7 will start with like 0.5, and then the next digit after 5 in 1/7 is 57. And then we repeat back to 1, 4, 2, 8, and this is our repeating block. And then you just keep on doing that. Okay, awesome sauce. So I would highly recommend y'all remember this chart, and it will be in the final thing if you didn't look at it or didn't copy it down or anything. Okay, awesome. Cool. So now we're going to transition away from fractions, percents, and decimals and talk about probably one of my favorite topics, bases. So bases are really, really cool. For those of y'all who don't know bases, that's okay. We actually work in the base 10 system. So when I say base 10, I think we actually kind of talked about breaking numbers up before, and someone said this was their favorite topic. So let's see if we can get some answers here. When I have the number 27, how can I write this in terms of place values? 2 10s and 7 1s. Awesome. Avyukt and a lot of other people. Y'all are typing really fast, so I can't call out all your names. So I can write this as 2 times 10 plus 7. Now, what about 365? How can I write that in terms of place values? Yeah, I can do 3 times 100, or 3 times 10 squared, plus 6 times 10 plus 5. And so what we're doing here is we're breaking the number apart into its place values. So we work in base 10, so our place values are powers of 10. But we can work in other bases as well. We can work in a base 2, we can work in a base 3, and so on. Now, the way bases work, bases are kind of just a different way of writing numbers. So in this case, we're writing everything in terms of like powers of 10. But we can write everything in terms of powers of 2 or in powers of 8 or something like that. So let's kind of like take a look at some sample bases. For example, let's take a look at binary. So binary is base 2, and this is probably the most common base that you'll see. So we'll take a look at how to convert to binary. So in binary, we start with 2 to the power of 0. And then we go, our next digit is 2 to the power of 1. The next digit after that is 2 squared. And then 2 to the 4th, or actually after that is 2 cubed. And then 2 to the 4th. Now, actually, if you look at base 10, we start in the ones digit with 10 to the power of 0, right? Because 10 to the power of 0 is 1. And as you see here, our ones digit, 7 and 5, we're multiplying all of that technically by 10 to the power of 0. Now, my next digit after that is 10 to the power of 1, and that's why you guys started doing 2 times 10 and 6 times 10. And then after that, I have 10 squared, and that's why y'all did 3 times 100, because that's 300. So after that, I can get to 10 cubed and so on, and this is where my place values comes from. I have hundreds and tens and thousands. And just like that, in base 2, I have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. So yeah. Now, in base 10, here's a question for you. Can we have a digit of 0? What do you guys think? Yes. Okay, can we have a digit of 1? Yes, good. Can we have a digit of 7? Yes. Can we have a digit of 9? Yes, good. Can we have a digit of 10? No, there is no digit like 10, because once we hit 10, we move on to the next place value. So that next place value is 10 to the power of 1. So instead of writing a digit of 10, we just write 1 in the second place value and then a 0 followed after that. And so the same thing happens in base 2. So in base 2, can we have a 0? Yes. Can we have a 1? Yes, good. Can we have 2? No, that's correct. We can't have 2 because 2 is another place value. So if I wanted to write the number 2, I would put 1 here. Or actually, hold on. I kind of like did this backwards. Let's see if we can make that a little bit clearer. 3, 2, 1, 0. Okay. So if I wanted to write the number 2, I don't write a 2 here because I can just write a 1 here. Because remember, 2 to the power of 1 is 2, and I have 1 of that 2. So 1 times 2 gives me that total value of 2. And then I put a 0 over here. So does that kind of make sense how we're able to represent numbers using different place values? Yeah? Okay, let's take a look at some other examples. So, can you guys express 9 in base 2? What is 9 in base 2? Okay, I think I see 101, 1010, 1001. I think those are the only answers I see. Good. So let's take a look at each of these. So remember our last digit has a place value of 2 to the power of 0, and then after that we have 2 to the power of 1, and then 2 squared. So 101 is basically just 2 squared times 1 plus 2 to the power of 0 times 1. So what is that? What is that sum? Good, it's 5. That's absolutely correct. Now let's take a look. So is 5 equal to 9? No, right? So that first answer isn't correct. But I'll leave the work up there because it shows us how we can convert from base 2 to base 10, which is still important. Okay. By the way, I'm writing that subscript of 2 to show that we're in base 2. So that should hopefully help you guys. All right, now if we take a look at the second one, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and then 2 to the power of 3. So I have 2 cubed times 1 plus 2 to the first times 1. Now what does this sum equal to? It's equal to 10. Good. 2 cubed is 8 plus 2 to the first, which is 2. So 8 plus 2 is 10. Good job. All right, and then this last one, I have 2 cubed times 1 plus 2 to the 0 times 1. So what is that equal to? It's 9. Perfect. And so this is actually equal to 9 in base 10. So 9 in base 10 is equal to 1001 in base 2. So yeah, once again, that subscript shows that we're in base 2. Okay, look at that. You guys just converted your first decimal number into another base. All right, so we're going to try a couple more examples before we move on to something a little bit more difficult. Yeah. Okay. Let me kind of clear this up so y'all have a little bit more space to like see things. Okay, so we're going to start off with, actually, I want to change colors before we do any problems. Let's do like a magenta. Okay. Can you guys convert 45? Or actually, wait, first of all, 45 is not a base. So we can you guys convert 19 in base 10 into something in base 2? And then also, can you convert 19 in base 10 into something in base, let's say 7? Use the same logic to see if you can convert into base 7. Even though we haven't talked about it, the logic is the exact same. Okay, awesome. I think I see Danush putting 10011. Yeah, and I see almost everyone else putting that. So let's go ahead and check this. So first of all, we can rewrite this as 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 cubed, and 2 to the 4th. So I have 2 to the 4th times 1 plus 2 to the 1st times 1 plus 2 to the 0 times 1. So what is that sum? 25. Or not 25. Hold on. It's not supposed to be 25. It's 19. You guys should be getting 19 because it's 16 plus 2 plus 1, and that's 19. Awesome. Or I proceeded to write 16. Sorry, 19. There we go. And some of y'all might be wondering, okay, like where did these 5 digits come from? Well, the process to convert from base 10 to binary is to repeatedly divide by 2. So if I do 19 divided by 2, I get 9 with a remainder of 1. So my last digit is going to be 1. Then I divide that quotient 9 by another 2. So 9 divided by 2 is going to be what? 4. 4 with a remainder of 1. So I write down that 1, and then I divide 4 by 2. What do I get when I do 4 divided by 2? 2 with no remainder, so I'm going to write a 0. What do I get when I do 2 divided by 2? I get 1 with a remainder of 0, so I write down another 0, and then I write down my last digit of 1. So this is my final answer. Awesome. So hopefully that gives you guys a little bit more of a clear method of how we convert to bases. And then looking at base 7, I see a lot of people saying 25, and that is absolutely correct. If we do 19 divided by 7, we get 5, or we get 2 with a remainder of 5. So that means 5 is our last digit, and because we can't divide that 2 again by 7, that is our first digit. And so that's our final answer. Okay, awesome. So you guys are doing really great converting from different bases to the decimal base, which is base 10. So yeah, we're gonna do a little bit more. Actually, hold on. Vaivehi asked, can any number be written in any base? Yes, any number can be written in any base, which is the power of bases. We're used to working in base 10. That's why we only think in base 10. But if you ever go into like computer science, you'll see people working in binary, base 2, or hexadecimal, which is base 16. Those are also very popular bases. Also, actually, if you guys ever work with like numbers, or actually, sorry, not numbers. If you guys ever work on like Google Docs or images and stuff, and you're trying to like pick a background color or a text color, if you select your color, you'll see like some weird series of digits at the bottom. But if you actually look at those digits, that's actually written in hexadecimal, and it's a hexadecimal version for your color. So it's like a color code, and that's normally written in hexadecimal. So that's something interesting if you ever like working with like Google Docs coloring. Awesome. Okay, Pranav, you want to ask your question?
So how do you get the 2 in the 19? How do
Oh
you
yeah,
get
so for the base 7?
yeah.
Okay, so first we divided by 17, and then we got a 2 remainder of 5. So we wrote 5 as our last digit, and then normally we would divide 2 by 7 again, but because 2 is less than 7, there's nothing to divide, so that becomes our first digit. So anytime, whenever you end with a number that's less than 7 as your quotient, that's your first digit. Does that make sense?
Yeah, okay.
Okay, awesome. There is no base 0 for those of y'all asking. Base 0 is not a thing because 0 to the power of anything is 0, so you can never express a number like that. Okay, so we'll do one last property with bases. So you can actually convert from different bases. So like you don't always have to do this in base 10. For example, I could convert from base 2 to 7 if I really wanted to. I mean, it would be horrible, but I could do it. But this is actually more useful for things where bases are exponents of each other. So for example, I can convert from base 4 to base 2. And you might be wondering, like, how do I do that without converting to base 10? Well, you kind of have to think about how base 4 digits are written. Now, every base 2, well, okay, first of all, base 4 is an exponent of 2, right? It's 2 squared. So we should theoretically be able to write base 2 numbers into base 4 numbers. So let's take a look. We'll start small. Can you guys write can you write 3 in base 2? What is 3 base 10 in base 2 form? It's 11. Good. Now, what is 3 in base 4? Good. It's just 3, right? Because 3 is less than 4, so I can actually write it like that. Okay, cool. Now, let's take a look at 23. What is 23 base 10 in terms of base 2? What do y'all think? In terms of base 2, what is 23? Make sure you guys check how many digits you have. I see a couple people with 5s and 3 digits. Make sure that your number actually adds up to 23. And then also when you're doing the repeating division method, remember that your last quotient should be your first digit. So you should never put in a number starting with 0. You should have a 1. Okay, I see 1, 0, 1, 1, 1. Okay, let's take a look at this. So this first digit is 0, 1, 2, 3, 4. So we have 2 to the power of 4 times 1 plus 2 to the power of 2 times 1 plus 2 to the power of 0 times 1. Awesome, sorry. And that's going to be 23. Good, awesome sauce. Now, can you write 23 base 10 in terms of base 4? You guys do that conversion? Oh yeah, I did forget to do the power 1. Thanks, Behi. Appreciate that. While I'm fixing that, can you guys do 23 base 10 in terms of base 4? Pranav, check your math. You're close, but not exactly. Okay, yeah, I see a lot of people putting in the answer now. It's 113 in base 4. Now, I see a lot of people putting 13. You guys are close. Just don't forget, you got that last quotient of 1, so that has to be your first digit. Okay, perfect. So if we check this out, we get 4 squared times 1 plus 4, whoa, hello. 4 to the first times 1 plus 4 to the 0 times 3, and that is indeed 23. And so you might be wondering, like, okay, well, I don't know why she made us do that. She made us find it out for 2 different values. But if you look really, really closely, there's kind of a pattern between each of the digits. So if I look at 10111 base 2 and 113 base 4, take a look at these last 2 digits. What is, oh, wow. What is this in base 4? 1 is 3. Good. Yeah. So that matches up. What is 0 1? 0 1 is 1. Good. And then this 1 matches up with a 1. So actually, if you look at it, it's very easy to convert from base 2 to base 4 or base 4 to base 2 because the numbers are related in pairs. So for example, if I have 132 in base 4, can you guys predict what this would look like in base 2? How can I write these last 2 digits first? How can you write 2 in terms of base 2? Yeah, Rob, that's absolutely correct. It's 1 0. How can you write 3 in base 2? 1 1, perfect. And then how can you write 1 in base 2? Just 1, right? And so this is our number in base 2. Isn't that so neat how we're able to convert so easily? I never had to find out what this is in base 10. I wanted to, if I could, I wanted to. But to convert from base 4 to base 2, very easy. In the same way, I can convert from base 2 to base 8. I can convert from base 5 to base 25 if I really wanted to. So you can convert very easily between places that have like bases with exponents. Okay, awesome. So that's where we're going to end for today. If you guys have questions, feel free to stick around for like 5 minutes before I have to head out. But thank you all so much for joining me in the 4-week number sense course. I hope you learned something a little new, and I hope you are able to use these strategies in the number sense. Yeah, thank you all so much. I had a great time. I hope you guys had a great time as well. And I hope to see you in the future in more advanced number sense courses. So keep an eye out for some newer courses. I would love to see you guys all again in the future. But for now, bye everyone, and thank you so much for coming. Awesome. Bye Danush, bye Sharanya. Awesome. Bye Avyukt. Bye Aryan. Bye Malvika. Bye Shri. Bye Sandy. Bye Myra. Awesome, awesome. This is great. Yeah, Muktika, do you want to go ahead ask your question?
So if you sign up for the one like the program next, what day will it be?
That one we'll have to see. We're still planning that one out, but that information will be out soon.
Okay. And my name is pronounced Mauktika.
Muktika. Okay, wow. I wish you
Yeah.
corrected me
You
earlier
got it
because I've been
first
calling you
try.
the wrong thing all along. Oh dear. Okay, I'll remember that in the future for sure. Muktika. Okay.
I'm sorry I didn't tell you first, but
No
you
worries.
did
That's
it
totally
first
okay. I'm
try.
glad I know
You
now. I'm
literally
glad I
said
know
it first try.
now.
Most
Wow,
people
that's
they would
interesting.
take like 10 tries.
Oh my gosh, that's funny. All
Okay,
right, well, I
bye.
will definitely remember your name, but thank you
Okay,
so much
you
for being
too.
here. And I hope to see you soon. Bye.
They'll help. These strategies will help me a lot. Bye.
Oh, awesome. That's nice to
Bye.
hear.
Bye, Bobby.
Bye bye. All right, bye-bye.
Can you explain the relationship between base 2 and base 4 digits again?
Yeah, so when we're converting from base 2 to base 4, first of all, hold on, when we're converting from base 4 to base 2, each digit in base 4 we want to write in base 2 representation. So for example, if I have a 2 in base 4, I write that in base 2 as 1, 0, and that takes my place at the end of the number. Does that make a little bit more sense?
Yeah.
Okay, perfect. All right, awesome. All right, bye-bye. And then also bye, Shriram. It was so nice to hear from you. Oh yeah, Simonvi, go ahead.
So, is a non-terminating number always an irrational number?
Yes. Or okay, actually, sorry, no. So non-terminating, look at 1/3, right? 1/3 is 0.3333 going on forever. That's non-terminating, even though it's a fraction. So non-terminating just means that like you can't express it as a finite decimal. Like your decimal has an infinite number of digits.
So it just keeps on going on and never stops anywhere.
Yes, that
Okay,
is correct.
thank you.
Of course. All right, awesome. For those of y'all still here, if you guys have no more questions, I will go ahead and end the meeting. But thanks y'all so much. All right, bye everyone.